Раз, два, три. Дорогие друзья, занимайте места в зале. Напоследок мы приберегли очень интересные доклады. Как вы уже, наверное, догадались, раз вы сюда выбрали прийти. И сейчас Андрес расскажет о всяких интересных вещах, которые происходят внутри Postgres. Надо понимать, что, в принципе, в команде Postgres люди занимаются разными вещами, но вот те самые штуки, на которые тесно завязан весь хайлоуд, который мы все очень любим, и когда база данных бессонными ночами админов справляется с миллионами запросов в секунду, это все вот как бы происходит глубоко в потрохах Postgres, и Андрес один из тех людей, которые очень плотно разбираются в этих вещах. То есть максимум низкоуровневого хардкора можно у него спрашивать, узнавать, и он реально тут один из тех людей, кто этим занимается. Поэтому, так сказать, прошу любить и жаловать, и всяческие вопросы, я думаю, и погоды в конце, и после приветствуются. Давайте поприветствуем Андреса. Actually start and welcome.
Thank you. So I want to talk about how to make Postgres more scalable and what steps we have already taken on the way there. And when I am talking of scalability right now, I mean vertical scalability, what means I'm not talking about making Postgres scale over multiple machines. I'm talking about making it faster on existing hardware or on use more larger systems more efficiently. I think horizontal scalability is also very important, but it's just a very different set of problems. And there's also systems where scaling horizontally in an efficient way is very hard, because if you scale horizontally, you have many more issues with latencies between the system. You have often duplicated data between the systems. So there's a good reason why you still want to scale individual nodes to a larger degree. One of them is that at the moment we see, or in the last couple of years, that the number of cores, CPU cores in a single system has increased quite dramatically. So just looking at the cores, not the number of CPUs itself, in 2005 there was the first x86 CPU with 2 cores. Now we are at 18 cores, and there's already ones announced with 32. So that's the single CPU, and then you can have servers with up to 8, and there's some hacky ways to go beyond that, different CPUs. So you have 8 times 18, that's a large number of cores. And then each of these cores have hyper-threading. So all of that is not that easy to deal with from a software point of view. For a long while, Postgres has claimed that we are good at scalability. We are perfect, we don't need to do anything. That claim has been made for like about 10 years, and then somebody ran a benchmark, and yeah, it wasn't really the case anymore. Apparently, hardware from 10 years ago is not the same as hardware from today. So since then, we've had in a couple versions worked on the performance of Postgres, especially the scalability, which means we weren't focusing so much on making an individual query faster. We were working on making 100 queries running at the same time, or 10 queries running at the same time faster, which is a different set of problems. Sometimes they overlap, but not all of the time. And there's a couple things you have to be aware of in modern systems to understand what the set of problems are. And one of them is that in bigger systems today, we don't have uniform memory access anymore. That's called NUMA. It's non-uniform memory access. So in the good old world, where in the early multi-CPU servers, we had a CPU and another CPU, they were on the same motherboard, and they had a common bus accessing the hardware, access to the memory. And it worked if a CPU needed some memory, what it did was say, hey, I need memory number X. And then that went on the bus, then the memory controller replied, okay, here's memory so-and-so, and then it was shipped back. That works well if you have a small number of sockets, but it means that the bus is shared between those CPUs, and there's conflict between that. So because they share the same bus, the speed is limited. So what we have today, that existed since the 70s, but commonly today, we have an architecture like this. So if we have the same amount of memory, we have a CPU, and this CPU has its own bus to the memory, and the other CPU can't access that directly. Instead, when CPU 2 needs access memory from CPU 1 that's attached to CPU 1, it has to ask CPU 1, hey, can you please give me the memory at that location, and then that memory gets transferred. Which is obviously, it's going to be faster if you don't need to do that. So that alone presents quite a lot of performance problems because it takes like 3 to 5 times longer. In a 2-socket system, if you have an 8-socket system, it can be 12 times slower to access another node's memory. It depends on which of the other nodes it is. So you have to be very careful about latencies when accessing memory. Yeah. Another common problem which few people really understand, which I'm not going to go into depth too much today because it would fill a half-day talk in its own, is that there's a problem keeping these this memory and the caches around the memory coherent. Which means if you have a system like this and CPU 2 asks for memory on CPU 1, then it transfers that and it doesn't have any own memory, so it keeps it in its own cache. But what happens if now CPU 1 also wants to modify that memory? It needs to know that it has to go to CPU 2, get that memory back because it might have been modified, and that's a large amount of bookkeeping you have to do. And that has a lot of overhead, but it's also not just the overhead that makes it complicated, it's more that that can actually cause correctness problems, because you're not guaranteed that everything happens in order. Because if you would guarantee that everything happens in order across 8 CPUs, then it would be pretty much often the same speed as if you had one CPU, which obviously is not good. So the CPUs do a lot of stuff out of order, and they just simulate being in order. But there's loops in that simulations, holes in that simulations, where you can see results where you think, oh, that doesn't make any sense. But yeah, you were just not careful enough. So, in Postgres, a lot of the performance problems we've seen were related to locking, and to understand what that means in Postgres, there's a couple different types of locks. And I'm going to start with the lowest level one, that's a so-called spin lock. Probably some people here have heard of spin locks. Who has? Okay, that's a good number. So Postgres uses a relatively simple spin lock implementation, and that's because we tried using like pthread locks, and the overhead was just completely far too high. And even using something like Citus on Linux, if you are running contended, the overhead is quite noticeable. So it's just a simple spin lock in user land with some backoff if somebody knows what that is. And what's very important for a bunch of the performance problems coming on further is that a spin lock is, the way we have them, is just an exclusive lock. That means there's no like a reader lock where several people can hold the same lock at the same time. And which also super important is that there's no queuing, which means if you wait for the lock, there's no saying, hey, please, other process, wake me up. You just try again, try again, try again. Then if you try often enough, you sleep a bit and then try again, which means it's not very efficient to block very long on a spin lock because all the CPUs are going to be constantly busy. And very important is that there's no deadlock checks. You can have, if you acquire 2 spin locks in an order that's not consistent, you will deadlock and nothing will ever happen. The only thing you can do is kill 9 new Postgres, which is not very nice. So you have to be very careful when using spin locks. And there's also no error recovery. So if you kill a process while it holds a spin lock, yeah, well, it will still hold the spin lock. And again, kill 9 is the only rescue. So these have to be used in a very careful manner. It's not something normal you use every place you need a lock. The next, a bit more complex type of lock is the so-called lightweight lock. It's not that lightweight, but yeah, the next one will be heavyweight lock. So they're lightweight. They're still rather fast, and the important difference is that they're reader-writer locks, which means you can acquire them in a shared mode. So 10 people can hold the lock in shared mode, but nobody can at the same time hold the lock in exclusive mode, and obviously only one person can hold a lock in exclusive mode at the same time. And also it's important that they have error recovery. So if you have an error while holding a lock, the lock will be released. So that's very important for some of the use cases. And they're fixed numbers, so basically at program start you need to know how many locks you need. You can't just dynamically add them, which is important because consider a database where you would need to declare how many the number of tables it can have because there's only so many locks that exist, and the locks have a fixed name, so there's no lock for LW lock for a specific table. And they internally use bin locks, and that will be very important in a moment. We'll see why. And then the most commonly used type of locks on top of that is these so-called heavyweight locks, and those are the locks that we acquire when, for example, you do a select from a table that will internally acquire a lock on the table, and that will be held for the duration of the transaction. And same if you do an alter table, it will acquire an access exclusive lock on that table and will be released at the end of the transaction. And there's a bunch of other cases where you also use these heavyweight locks that are not directly related to database objects, but generally that's the case. They are related to some database object, and that means there is not like pre-assigned locks for each specific object. Instead, there's basically a hash table of possible locks, and then you can, if you define how what your lock identifies. For example, you say, I want a lock for the for the table in database 1, and the table has the OID 7, and then that would be the lock identity, and then you look up which part of the lock table would be assigned to that, and then that's the lock. And to make that consistent, that internally uses LW locks and spin locks, but the second part is new. So, the way this works is that if you have a backend, it will go and it wants a heavyweight lock. It goes and locks the lock table. I'm going to glance over a couple of details here because the exact details aren't that important. We have a bunch of efficiency hacks to make it much better, but that's the basics. And once we have that lock on the lock table, that's an exclusive lock in this case. We can find which position in the lock table is assigned to our lock that we want to have, and the lock is defined by the OIDs, and then we can acquire the lock. And that's fine, and then we can release the lock on the exclusive lock on the shared lock table. But you can see that even for acquiring shared lock, we need for a short time an exclusive lock on the shared lock table, which means it will scale not that good if you have 20 backends acquiring shared locks on the same table, even though those locks are actually not exclusive. There's a short period of time where that cannot happen at the same time. Yes?
Which kind of lock is used to lock table? Lightweight lock?
No, heavyweight locks. Because they have to you can have many of them, and the database, the name of the table cannot, at the start of the database, be assigned to a specific lock. So that presented a problem because we were pretty slow if you had many of accesses to the same tables in many different connections. So Robert Haas in 9.2 had a pretty cool idea. I find that very, very elegant. Instead of always acquiring this exclusive lock on the shared lock table, he observed that for many types of objects, we only ever acquire locks that don't conflict with other locks. For example, if you acquire access share lock, the lowest lock on a table, it will usually, in the majority of the cases, not have a conflict with another lock because you very rarely actually exclusively lock tables, and the table locking performance will not be the problem if you constantly have your tables exclusively locked because the other backends can't do anything anyway. So there's no concurrency problem. So the idea there was, hey, we have a lock, and then we decide, is this a lock that's likely to conflict? And if it's not, what do we do? Instead of going to that shared lock table, we just say, hey, we now hold this lock. Very easy. And don't go to any shared resource. We just say, we now hold this lock. Obviously, we need to do something more, because if everyone does this, then there would be no locking, which would be pretty pointless. Then we could even optimize that away, even if that is very cheap, because we only use session local data, it's still not free. So, but what happens if somebody acquires an exclusive lock? Exclusive locks, as I said, are pretty rare. So what we do is, if you acquire, notice there is an exclusive, you want an exclusive lock, we go to each of the other backends and check, hey, does any of these backends have a lock that's conflicting with mine? So we go to backend 1, check, oh, there's a lock on that, but it's a lock that doesn't actually conflict with mine, because it's a read-only lock. I will want to only block other writers, so it doesn't actually conflict. Then I go to backend 2, check the same, backend 3, check the same, and after that I can say, hey, great, and now I make an entry into the shared lock table, because it's a so-called strong lock, and have the lock. Obviously there's a lot of internal things about how to do that correctly. I'm glancing over lots of details here, but I find that a very the basics here are a very important idea when optimizing concurrency. It's if you don't need to access a shared resource, it can make sense to make the common path faster on the expense of the slower, which to make some other parts very slow in comparison, because it happens so infrequently. So that's the result of this optimization. I did this on the current Postgres master. I removed the old optimization, and you can see that even at the low number of clients, you see the differences. Even at 8, there's already a noticeable difference between the not using this fast path locking technique and the other one, but at high number of clients, you can see this is a massive difference. And this is only on 2 socket machines. And it's a read-only workload that completely fits in memory. If you had constantly hit disk, you probably won't see that high number of transactions, because you don't have a million transactions. That's not something you hit on disk, but yeah. So that was a pretty massive difference. I've run this in the past on a 8-socket machine. The difference there is even bigger. So I think that was a pretty cool optimization. Took only, I think, 250 lines of code. So you can do with small local changes, you can make large differences in scalability. One interesting bit is that if you ran this with 9.1 against 9.2, the difference would be much smaller, because there were other bottlenecks that we would be hitting. So in there, the difference was more like on this, on the 2 hubs, a difference of factor 2 or a bit lower. But since we also got rid of other bottlenecks, this is the prime bottleneck now. So I think that was one cool optimization. So up to the next. Who has run a perf profile on Postgres because of performance problems? Who has seen a profile that looked like this? So I've seen that a bunch of times. I've been up to 99.7 or so. Yeah, so that's not fun. Obviously, spending all your CPU time in a spin lock, and that was what slock stands for, is not good, because we could actually do something useful. Yeah. In this case, we really only spend time in the spin lock and in the LW lock code. And then there's some other code that comes much later, but we are already below the %. And it's also interesting to see none of that time is spent in the kernel, so it's really just Postgres' fault. So we unfortunately have to read a bit of code to understand this. I've greatly simplified the code. It's about 300 lines in the real world, but yeah. So it happens to, after profiling this, I noticed this is only happening on shared locks. It's not actually exclusive locks, it's shared locks that are the problem. But then you wonder, but wait, shared locks should be no problem, because you can acquire them from several sessions at the same time. So why is this causing this much trouble? So it turns out that LW locks for a long time have used the spin lock internally to protect their state. And if you remember earlier, I mentioned that spin locks acquire an exclusive lock for the time of their duration. So what we do is, if the lock is shared mode and there's no exclusive lock, oh, there should be an unequals. Yeah, there should be an unequals here. I simplified the code too much, apparently. But yeah, if there's no exclusive lock, that's what it should say here, then you can just say, okay, we acquire the number of shared lockers, and if there is an exclusive lock, what we do is to say, we add ourselves to the wait queue, and then we release for the spin lock, and just go into waiting in the kernel. And that in Postgres is implemented using semaphores. So that part is actually quite efficient. And then we just retry once the lock has been released, because somebody else could, in between, since we've been woken up, somebody else could have acquired the lock at the same time. So we just do the same dance over and over again. Does anybody see the fundamental problem here?
Shared locks. I mean, it can never execute. It can never reach to the exclusive lock state. No player locking.
Yeah. So the problem is that once the spin lock here is, even if you have a shared lock, there's only one backend can do this. Even if all of them can actually continue because the lock would be free. It's worse than that though. Consider what happens if you hold the spin lock and then go to sleep, which is the big argument against spin locks. But on the other hand, then you hold the spin lock and nobody else can do anything. And then consider what happens if you have a system which is overloaded, where everybody is waiting in the CPU. At some point, all of the backends have to be put to sleep because there's more processes running than you have as cores. So at some point, they will just go to sleep in here, which is not very fun. So if you do a profile on a 4-socket machine, which is what I had available, just on a scale of 100 and a read-only PG bench, this is what you get. You see at the beginning it scales somewhat okay-ish, and at a certain number of CPUs, clients, you just see a very sharp drop-off. And that's where you see that most of the time is continues being spent in spin locks. And it's very important to know that PG bench is actually a pretty easy workload in comparison. If you have a workload that has like lots of nested loops and accesses in very short succession a lot of pages, then you can get this at much lower number of clients. And I have not been able to reproduce this problem on anything but multi-socket systems. I'd be curious if anybody has reports of spin lock contention on a single-socket machine, but I've not been able to reproduce that. So, obviously we need to do something to fix this problem, because, yeah, scaling like that is not nice. It would be fine, or would not be perfect, but it would be fine if you start, like, just not growing anymore. But, like, shrinking rapidly when the load increases is not good, because that will just exacerbate your problem. You will have more and more clients processing queries. So, what can we do instead? We can try to use atomic operations. Who here does not know what an atomic operation is? Oh, cool. That makes it easy. So I've implemented this before. Postgres had an atomic abstractions library, but Postgres runs on a lot of different platforms. Unfortunately, not all of them provide atomic operations, because for some reason we, for example, run on DNS, on HPPA. Does anybody here know what those architectures actually are? And so, no, they don't really have atomic operations that you can use in user land. You can do some tricks in kernel, but fortunately not running in the kernel. So we had to write an abstraction that provides atomic operations, even if the hardware doesn't actually have atomic operations, because we didn't want to maintain code path for hardware that has atomics and another one that doesn't. So we now have atomics that fall back to spin locks on the very few platforms that don't use have spin locks or have atomic operations. So then we can use atomic operations to modify the lock counts, if only when using a shared. Yeah. So what we just do is we just check whether the lock is actually free, and if it's free, we just acquire it. We just glance over that, because that part is easy. But what you can't just say, hey, I'm saying shared plus, because if you do that, you would potentially run into a problem. So consider what happens if the lock is busy. So atomic lock require return true, in which in our case just says, hey, the lock is not free. And then we enter ourselves to the wait queue. And what would happen if we just went to sleep directly after the queue here? What could happen is that in between the queue and in between waiting on the queue, somebody else could actually have released the lock, and we would just wait for somebody to wake us up, and then when somebody doesn't actually exist, which would obviously not be good. We could do some nasty stuff like retrying every millisecond or so, but that would not be very efficient. So what we instead do is a somewhat nasty thing, but it works. We enqueue ourselves in the wait queue, then again test whether the atomic lock is now free. And if it's not, then we go, if it's free, then we go, sorry.
I'm afraid that I forgot not again.
Yeah, I noticed. Sorry. You shouldn't write pseudocode. But the other code was far too long for the slide, so I had to write some pseudocode. So if it's free now, then we go and unqueue ourselves, and because now we got the lock. And if it's not free, we know that now we would be woken up because we have already been enqueued. And every time we are queued, every other person that unlocks the lock will have to wake us up. So that's now race free, and then we just retry again. So there's a lot of more complexity around this because this is only for shared locks. If you add exclusive locks to the mix, it gets more complicated, but basically that's the trick. And yeah, I spent like, for the first version, I started looking at an issue that we had from a customer at like 2 o'clock in the night, and I actually had something in the morning that worked. Yeah, so that's different between the old and new. And that's exactly what we want to see. So at the beginning, we are staying the same because the lock contention is not actually the problem. But instead, once we hit the place where we already hit this cutoff here, we just continue to scale a bit, and then at some point we run into the cutoff where the system hasn't actually had more compute resources, because this is a 4 times 8 cores system. At some point, you're just not going to be faster by adding more clients because all CPUs are 100% busy. But this looks much better than this. So, any questions so far? So, one other problem here, I have to unfortunately go again into a bit of the internals. Postgres has so-called shared buffers. Does everybody know what a shared buffers is, or anybody not? Okay, so Postgres doesn't want to go to the disk every time you execute a query. Instead, it caches the blocks in memory. And, oh, you know? Oh, sorry. Okay. So what it has one large array of so-called buffer tags. And that's just the basic definition with some complex stuff stripped out. And that basically knows it has a tag, which is the information, which disk block do I have in that buffer. Then it has some flags, and then, very important, it has a so-called usage count. And that's, I'm going to explain in detail what it's about, but it's for knowing which page to evict if you don't have any free buffers anymore. Because if your workload is 100 gigabytes and your shared buffers is 10 gigabytes, obviously you can't have a buffer for every on this page because, yeah, they exist now. And then, which is also very important, we have the so-called ref count. This is how many people actually use the page currently. And these fields are protected by a spin lock. And then we have actually a second array, which is just the same number of entries than this one, which actually contains the data. So there's, by default, just an array of 8K entries, and that contains the actual data. So this is not stored in the same place. So if we need a page to execute a query, for example, because we had just a sequential scan of a table, we said, okay, we need a page for the first entry, for the first page of the disk table. Then we go into shared buffers, and shared buffers basically looks like this. In case I had set shared buffers to 20 or to, yeah, just normally you set it to, these days you set it to a number of megabytes or gigabytes or so, but in the end it's converted to a number of buffers you have, just by dividing it by k, or by whatever page size you configured. What happens then, we acquire a lock. In 9.4, what happens is that we acquire the so-called buffer free list lock, and that's a lock we acquire in exclusive mode. So nobody else can do what we do at the same time. So they all can access pages that are already in buffers, but they can't find new victim pages. The victim page is called victim page because we remove it from the cache and replace its content. So it's thrown away, so that's why it's a victim. What you do is, so we acquire this exclusive lock, then we go and say, the page at place 0, does that have a usage count, a ref count of 0? Because if a page is used right now, we can't reuse it because the other one might have this pointers into the page, so that would not be nice replacing it. The next thing we do is check whether the usage count is 0. If the usage count is not 0, we say, okay, we can't reuse it now, but while we're looking at it, we now reduce the usage count by 1. And what that means that over time the usage count goes lower and lower, and to counter that, every time we touch a page, we increase the usage count by 1. So that's basically a simplified LIU. Does everybody know? Who does not know what an LIU is? Okay. So what we do is when we start is we check this page, check if it has a usage count of 0, we just use it, but if not, we go to the next one, we check page 1, eventually lower the usage count, and so on and so on. That can go on for a while. Potentially we go to the end and just notice, oh, we haven't found a single page with usage count 0, so what we do is we start again and do the same thing over potentially 5 times in normal case, because that's the highest usage count we will allow. As you notice, this is not really the most efficient algorithm, but in many cases it actually works great, because on average, some of the pages here that you start checking will be 0 pretty soon after. It's actually basically a simplified clock sweep algorithm, if somebody heard this. And for OLTP it works great. It doesn't work that great if you have like batch workloads, batch writes or batch reads. So this obviously didn't work very well. So the biggest problem here is there are 2 big problems. A, the algorithm by itself is inefficient because touching hundreds of thousands of buffer descriptors to find a single page is obviously not good. But what's even worse here is we do it while holding the exclusive lock. Nobody else can do this at the same time. So if this takes 10 seconds, which it obviously never does, but just assuming it takes 10 seconds, nobody else can read even a new page while that's happening, which is not very good. So we could write a more efficient algorithm for this, but it's actually not that easy to find one that's very good. So what we did is to just make this more scalable. We do something inefficiently, but we do it in a way that we can do it several times over at the same time. So instead of taking the lock over the whole thing, we now advance this one by one, and we just protect the variable that says, oh, look at this page next, which is called next victim buffer. And we just use an atomic add and just choose, hey, we can look at the next variable, and then all this process can happen. So backend 1 checks this page. At the same time, while it's still busy checking that page, the next backend can come and check page 1, and so on. So the sweeping of the clock, and the clock is basically going around here, then starting over here, going around here, and so on. This can now happen at the same time in several backends. So there's obviously, if you just did this here, you would eventually run increase next victim buffer to a place that's bigger than 20, which obviously would not be good, because then you would access a buffer that's too large and result in a seg fault or something even worse. But there's a relatively easy operation that we can use. We can just say, okay, after incrementing it, the victim buffer, we just take it modulo the number of buffers, and then suddenly, hey, it works efficiently, and we just access the text buffer at the start. So I benchmarked this like an hour ago. Again, a PG bench read-only, but as I said, you don't normally see this in a memory, in a workload that fits in memory, because you never need new vector buffers, because everything fits to shared buffers. So what I did, I used a different scale for PG bench, and the scale of 1000 results in a 14 gigabyte database, and I used 40 gigabytes of shared buffers. So obviously, the workload does not fit into shared buffers. And these tests have been done on an EC2 instance, and that explains some of the variance you're seeing here. The per run variance on EC2 is pretty bad. It's not fun, but I didn't have access to the big machine anymore, so I had to make do. I wasn't happy about it, but yeah. So on the base system, what happens, you can see that about 100 clients, you start seeing, hey, it's slowing down. And again, quite dramatically. If you have 700 clients, you're about the speed of if you had 5, which obviously is not good. So, but if you do the trick with just saying, hey, we do this with very granular locking just to protect the next victim buffer variable, we do better. Not perfect, because we still have a quite noticeable drop down in the end, but it's much better. So, I think these represent a couple of very different approaches how to attack scalability problems. We just, the first one was we avoided taking an actual lock on a shared resource by simply not doing it and making other cases less efficient. So that's a pretty good approach, and there's lots of literature about it. Another thing is we can just be better at locking. The LW lock stuff, we just take the same number of locks overall, but we just do it much more efficiently if you have shared locks. So that's also a good approach. It only takes you so far. At some point, again, the access to that single cache line where the lock state is stored will be a contention point again, because every time you say shared plus plus or exclusive plus plus, it has to be transferred to the next CPU. So you have access to that across all the nodes in the system, like sockets in the system. But it can take you quite far. The other thing is that you can use atomic operations for stuff which previously used locks. Sometimes you can just avoid taking any locks. Now, admittedly, on the CPU level, internally, doing an atomic operation on x86 is not very different from an actual lock, but the big difference is that there's no CPU scheduler who can interrupt in the middle of it. So it will just, at some point it will succeed, and you won't go to sleep while having an in-progress operation. That can make a large amount of difference. And then in the last example, what we did something inefficiently, but we didn't have the resources to make it efficient because it's actually complex. So what you do is we just make the lock that protected the whole thing much more granular. We didn't protect the whole shared buffers at once, we basically did it per single buffer. So we now have much more granular locking. So these are the ones that we have fixed a bunch of other issues, but I thought we need to select a subset here, because otherwise we'll never finish here with this talk. These are the ones that I'm aware of that are the biggest problem that are not fixed. Some of them are pretty easy to fix, others are really hard. So right now we have this so-called extension lock. If you insert something into a table and there's no space in the table because the file is just not large enough, we need to extend that file. We need to add pages at the end. At the moment that happens by saying, I'm not requiring the extension lock on that table, and then I'm looking for a new buffer in the shared buffers. Once I found that buffer, I need to write out the old contents to disk, and then I can finish extending the table. Obviously, that's not exactly good, because you need to write out data while holding an exclusive lock that prevents anybody else from doing anything. So that's pretty bad if you have like parallel copies that can make things to the same table, that can make things much slower. There have been a couple patches around this to make this faster, but it's not committed to 9.5. I think this is the by far easiest to fix here. Then the buffer replacement we just talked about, the one where you go through all the buffers. As I said, this is not very efficient. We just made it less bad, but we didn't make it good. So fixing this is mostly a research project because there's a large, all the algorithms out there have trade-offs that make other cases worse. So you have to do a lot of benchmarking, finding out which approach you actually want to use for your product. And we need to come up with something better because shared buffers is not a good thing if shared buffers is measured in billions, potentially. So this one is hard to do, but it's doable. Then I think the by far worst one is that in Postgres, so-called snapshots, I'm going to explain in a second what that is, are very expensive to compute. If you have a system that does a lot of queries, that can hit you pretty bad. And that's actually, if you go back to here, if you avoided taking snapshots, this would just have scaled pretty well. All the contention here is from around the lock that protects computing a snapshot. So what is a snapshot actually? Does everybody know what MVCC is? Good. So, to know whether a row is visible, Postgres consults a so-called snapshot, and that snapshot means when I started this query, what am I able to see? Which other transactions are running, which other transactions have committed, and stuff like that. This part of that data structure is on disk or in memory, and that's say XID, which is the transaction ID has committed or not. The other part is an in-memory structure where every running transaction has an entry in there, and that says I have the XID so-and-so, or I don't have any XID, or there is no backend with that number. But it says then XID 34 is currently running. And if I see a row that has been produced by XID 34, I don't want to return it because the transaction has not committed yet. So I need to gather that information somewhere, because what could happen is, at the beginning of a query, XID 34 was still running, but while I was processing the query, it committed. But I still may not return it as committed, because it wasn't committed when my query started. So what we currently do is, to fix this, is we lock the whole table in shared mode. It's shared, it's a shared lock. The whole proc array, that's what it's called, but it's an array of processes. And then we go linearly, or go through all the entries in the array, say, okay, the smallest XID in here is 13. Everything else before that has to have finished. I'm checking which one is the biggest one. Everything below, after that, cannot be committed when while my query is running, because, yeah, it hadn't started when I was starting. And all the runs in between, I say, these are the running XIDs. And then I release the lock. And now, whenever I want to see whether a row produced by a transaction, I say 27 is committed, I can say, go through that snapshot and say, xmin, it's larger than 13, so it might have already been committed. But it's smaller than xmax, so I can't be sure whether it has committed. Instead, I check whether it's in my running list, because it might have been committed in between. Bruce has a talk that details how this works in detail, maybe somebody has seen it. So, but going back, we see that we have an exclusive lock here. But that works well with the modifications to the LOV locks. That happens to be, many processes can do this at the same time, but on the other hand, this is not very efficient. If you have 1,000 clients, you have 1,000 entries in here, and you have to go through all of them, and then if they have sub-transactions, you need to do additional processing, so that's not super fast, but even then, that would still scale linearly, or near linearly. what's worse is that if, for example, transaction ID 34 wants to commit, what does it need to do? It needs to acquire an exclusive lock on the whole thing and change its entry. Obviously, lots of shared locks and exclusive locks at the same time don't mix, so you cannot compute a snapshot while a transaction is committing. On the other hand, it also has a problem that the exclusive lock on the back here in backend 1 doesn't actually have to lock out another transaction that also wants to commit, because there is no concurrency between two transactions committing. It's only around protecting against snapshots. So this is pretty bad. We have two rather wildly different approaches to fixing this. One of them is to use more complex locking. We don't need to lock everything at the same time because transactions can commit at the same time. So we can basically split locks into I'm protect against snapshot computation and I'm allowing committing. And we can do something. Amit Kapila had a talk at PGCon, and they basically said, I'm going to do work for all the backends that are waiting at the same time. So I'm basically batching work after I got the lock because I already have the lock. That helps also a lot. But all these don't basically do away with the fact that we have to scan a large array. And as databases get larger, as the number of clients increases, that's going to continue to be a problem. And about a couple of years ago, Ans Ansma reported, had proposed a so-called approach that's called CSN, commit sequence number, which basically reduces the size of this snapshot to a single number, which is very quick to gather. And that's a pretty cool approach. The problem is that it's also viciously complex. So my current thinking is that we are going to do some local relatively easy optimizations, making this faster, and at the same time working on making CSN actually doable. There's a team at UAway that is working on this, and they have pretty good results. If we remember that the earlier results on a 4-socket machine topped off at some point, they continued that linearly on a 8-socket machine to nearly the full capacity. There's still bottlenecks, and then other bottlenecks come up, but you can do a lot. So I think the patch is pretty not yet ready, but so there's also some good stuff coming. So then the last bigger bottleneck I'm aware of is that we have these buffer pins where you have this ref count in there. Every time you look at a buffer, you need to pin it into memory so it doesn't get evicted while you use it. The problem is that that is an atomic operation, and it's currently even worse than that. We use a spin lock, and as we know before, a spin lock is exclusive. No two backends can pin something at the same time. They can have it pinned at the same time, but the process of pinning is exclusive between these, which is not very good, because consider something that like a B-tree root page, which every time you process a query to the same table, you go to all backends go to the same page, pin it, and then continue. So having a short exclusive period in there is not very efficient. But it's actually doable to replace these mostly by atomics, and we can do some tricks by avoiding blocking altogether for some common cases. For example, in the B-tree root page case, we could, instead of doing modifying in place, we could switch to copy and write and just not take any locks. That will usually not be a very good idea, but on B-tree root pages, which are comparatively small in comparison to the rest of the index, that would be pretty good. So there's stuff we can do, and there's some smaller patches around it, so I think that's pretty good. What I would like to do now is, do you have any other big scalability, concurrency bottlenecks that you have seen in practice that I haven't yet talked about? So there's actually in 9.4, I didn't put it on my slides because I thought I would have less time than how much time do I have? Okay, so in 9.4 we are much more efficient now about this. I don't have the slides here, the numbers here on these in the slides, but we basically, the val buffers are now partitioned way. So several processes can insert into the val in the buffers at the same time, and then only wait till all the preceding ones have finished. And I have not yet been able to make val insertion a bottleneck in 9.5. So it would be interesting to see whether you have numbers that would still make it a problem. Unfortunately, right now I don't have access to an 8-socket machine. On the 4-socket machine I had access to until recently. I couldn't make it the bottleneck, especially with 9.5, where the CRC computations, which made it slow before, are now using the Intel. There's like a hardware instruction for computing CRCs, and we also made for older processors. We now use a slice by 8, so we compute more valid CRC at the same time. I would be interested if you see that still be a bottleneck.
Which version? 9.4 split insert lock?
Yes. So it has the insert lock optimization, but it does not have the CRC optimization.
And then 9.5 CRC optimization?
Sorry?
And which version has CRC optimization?
9.5. And yeah.
Okay, I can confirm that last patches in 9.5 improve read scalability. It's really cool, thanks. But it doesn't improve write scalability.
It actually does. I've benchmarked it as about a factor of 2.5, but it does some. It's not perfect yet. I'm not saying that.
Okay, it improves, but not yet cool. For example, the second problem is still here, and if you try to use Postgres with huge shared buffers, so that all the data would be cached with database, not page cache of operating system, you're getting troubles.
If it fully fits into shared buffers, no.
No, of course.
If some of it doesn't.
Yes.
But yeah, we desperately need to do that. If you're interested in working on fixing it, please come and do it.
Okay,
I listed these because I hope other people help.
Okay, I'm really interested. I probably can't write code, but I really appreciate to help with testing and benchmarking and other things.
The other thing is, if you don't have like the development expertise or something, help them with A, benchmarking, and B, hardware for benchmarking is very important, because I can write patches to do stuff, but if I don't have the hardware to say, hey, is this better or not, then it's not very good. I did some benchmarks on EC2, but the benchmarks results are so varying that it's very hard to say if this is better, unless your results are like 50% better, then you can say something, but anything smaller than that is, you need so long run times that it's not feasible.
There are rumors on hackers. I think that you should not set your shared buffers larger than 8 gigabytes, even if you have like 100 of gigabytes of memory. And the optimization of locking does not affect this limitation right now, I think. Yes?
It does to some degree, because now the eviction is more scalable, because you can do it at the same time. It's still not perfect. It depends really on why it's a bad idea. If you have a workload that fits 99% of in shared buffers, you can have huge improvements by setting shared buffers to a huge value. I've had it in production with values of over 128 gigabytes without any problems. There's some caveats though. If you have, for example, do very frequently truncate tables or very frequently drop tables, I'm not talking about temporary tables, but real tables, then it's not that a good idea. Because to find out which pages to throw away, what we do is we go through the whole list and compare every page where they actually should be evicted, because it's now where it's from that table. Not that cheap. So it's also not perfect. It really is workload dependent.
Thank you.
Have you seen on speed of PG writer? Does it do something efficient to leaking buffers?
I've not yet seen BGBuffer do anything useful. We should rewrite that thing.
I assume you are using a single atomic value to protect the pointer to the clock sweep, right?
Yes.
Or did you consider using multiple arrows? Suppose you just split the log using several variables and you have multiple instances of them.
Yes, it wasn't a big difference. I tried that. So what I think would be better than that is to say we don't increment the clock speed by 1 each time, but we increment it by 10. Because from what I've seen in the profiles, it wasn't actually the atomic operation that was the problem, but the bus lock of a shared cache line. So it's not the number, which cache line you touch, is that the number of atomic operations. So just saying incremented by 10 or 15 every time would be, it was better in my benchmarks, but currently the bottleneck is not that variable. The bottleneck is all the buffer headers, descriptors you touch. So we need the bottleneck. I don't think you can measure anything above 1% or 2% with that change, which is why I didn't commit it. We first need a more efficient diction algorithm, fundamentally more efficient before going there.
There is even theoretical limitation on the best possible algorithm that you can invent, right? You cannot just create a Go algorithm, right?
A less bad one, then, yes.
Yeah, and so we need to know what is the limitation. So suppose I have a workload that just fits in memory in 50%. What should I do? Should I create my buffer, shared buffers cache 10 gigabytes, 100 gigabytes? So well, I have a terabyte set of data. I have just 50 megabytes, 50 gigabytes RAM. Should I create my shared buffers to these 500 gigabytes or not?
It depends on how uniform your access mode is. If you have like completely random accesses, then it's probably not a good idea, but very, very few access profiles are actually completely random. Usually you have some non-uniform distributions. You have like 10% of the data is created 90% of the time, and if that all can stay in shared buffers, it's a huge win. Unfortunately, this is the right value kind of advice I can give you. The more skewed your access profile is, the better it is to have huge shared buffers. What you can do is there's the so-called PG buffer cache extension, and then you can see how uniform your usage counts are. And then if like there's a large deviation between the usage count values and they're well distributed across the whole size of shared buffers, then it's usually good to increase it further if it helps. If it's like all of them have the same value, all of them have 5, then it's usually, that indicates you have a very random access profile, or all of them are 3 or something like that. In that case, you probably don't benefit from a larger value.